Hello, in today's video I'm going to be talking about energy, power, and work as well as momentum. Specifically, I'm going to be looking at energy and conservative forces as well as momentum and force. So starting with energy and conservative forces, there are two types of energy. One of them is kinetic energy and the other is potential energy. Kinetic energy is essentially kinetic energy can be defined as the ability or capacity of a moving object to move another object, and it is given by the formula K is equal to 1/2 mv squared, where m is mass and v is velocity. Next, I'm going to talk about potential energy. So potential energy can be described as energy an object possesses due to its position or state of being. Potential energy can come in different forms. We can have gravitational potential energy, elastic potential energy, nuclear potential energy, and there's also electrical potential energy. So potential energy is often given by the formula, or one of the most commonly used formulas is U is equal to mgh, where m is equal to mass, g is the gravitational force, and h is the height. So now moving on to force and momentum. Essentially, the relationship between force and momentum states that at the rate at which an object's momentum changes is directly proportional and in the same direction as the applied force. So this can be written in a formula as force is equal to the derivative of power, which can also be shown as is equal to the derivative of m times velocity. This can be said just because of the formula P is equal to mv. This formula also reveals that when a force acts on a particle, it changes the particle's momentum. So this means that if a particle's momentum changes, a force must have acted on it. In other words, if no force has acted on a particle, then the particle's momentum will not change. Will not change. So now that we've got that established, I'm going to go ahead and apply these concepts to a real-world example from the AP exam multiple choice section. Today I'm going to be looking at question number 7, which I am going to read and diagram as I read. So 2 carts of equal mass are on a horizontal surface with negligible friction. Do I have enough space here? Yeah, I'll draw it over here. So we've got our surface here. This is going to be a diagram of figure 1. So cart A is approaching cart B, which is at rest, as shown in figure 1 above. So cart A is approaching cart B, which is at rest as shown in figure 1 above. Attached to cart B is a spring that is initially compressed, right there. At the moment cart A collides with cart B, the spring is released and pushes on cart A as shown in figure 2 above. So figure 2 can be drawn as this. Figure 2, we've got cart A here and cart B. So the spring is no longer compressed, and it pushes cart A this way and cart B that way. So the question is asking, which of the following correctly states what happens to the kinetic energy and the momentum of the two-cart system as a result of the collision compared to those quantities before the collision? So it's essentially wondering if kinetic energy increases or stays the same, and if the magnitude of momentum decreases, stays the same, or increases. So we know that the kinetic energy of the system increases because the total energy of the system should be conserved, as we saw when we discussed conservation of energy, conservative forces and energy. So since there is no energy loss for the system in the process, as the elastic potential energy that was initially stored in the compressed spring has now converted into kinetic energy. So again, this goes back to conservation of energy and just the idea that in a system, no energy will be lost, and it is possible for kinetic energy to be converted to potential energy or vice versa, but no energy will be lost in the system. So since there is no force, external force, so essentially we can say that the kinetic energy of the system will increase. So then we're going to go ahead and look at the magnitude of momentum. We know that there is no external force acting on the two-cart system, so the total momentum of the system should be conserved, and hence the magnitude of the net momentum of the system will stay the same. So we're saying here that kinetic energy is going to increase, but magnitude of, I'm just going to write it like this, momentum for short, is going to stay the same. And when we look at our options, we see that option B corresponds to this answer. Thank you.